so this is lecture 32A. This is one of two lectures for lecture 32 on the infinitesimal generator matrix, which is going to be one of the most fundamental matrices for continuous time Markov chains. Okay, so we're going to start this section with reviewing what we did last lecture when we talked about continuous time Markov chains. So basically what we said previously was that we start in state I, then we have a certain amount of holding time that we're going to stay in state I. So we say this holding time is exponentially distributed with parameter qi. So we would stay in state I for an average of 1 over qi time units. And then once we leave state I, we go to a new state, say state j, not equal to I, with some probability pji. And then once we're in state j, we stay there for some exponentially distributed length of time that has an exponential distribution with parameter qj, or on average we stay 1 over qj time units. And then we go to a new state k, etc., etc., etc. Okay, so we're going to think about this in terms of alarm clocks. And so we're going to think about alarm clocks ringing whenever we want to transition. So we're going to get what are called transition rates. So the transition rates are going to help us think about where we're going to move and when we're going to move there. So think about, we can go from state A to many different states. So assume we can go to state J, state K, etc., etc., etc. So assume that there is some kind of alarm clock associated with state J. So let's say we can go to state J from state I. We have an alarm clock, and we're going to say that it is the IJ alarm clock. And it's going to ring after some exponentially distributed length of time with parameter qji. So what we're thinking about is here we have a parameter associated with this alarm clock that's exponentially distributed with parameter qji, which means that alarm clock j, or alarm clock ij, is going to ring in on average 1 over qji time units. So when we first hit state I, we're going to start all of our alarm clocks at the same time. So if we can go to state J, if we can go to state K, if we can go to state L, etc., we're going to start all these alarm clocks at the same time. And they're going to be exponentially distributed, right? So it could be that one time state J's alarm clock goes off first, and another time state L's alarm clock goes off first. Whichever alarm clock goes off first, that's the state we're going to transition to. And so here we assume that the IJ clock rings first, then we move to state J. So once we're in state J, we're going to start this process all over again. So now there are certain states that we can go to from state J. So let's assume we can go to state 1, state 2, etc. from state J. Then we're going to have these transition rates called Q1J, Q2J. Basically, these are the rates at which those alarm clocks are going to be distributed. So we're going to assume that we can go to, let's say here, state 1 at a rate of Q1J, or my 1J alarm clock, or my J1 alarm clock is going to ring at some exponential distributed time with parameter Q1J. So whichever alarm clock rings, we move to that. And these QJIs are called the transition rates for the continuous time process. Okay, so we can get, from these transition rates, we can get the holding time for state I. So if we're in state I, and we can go to J and K, for instance, then and we can go to state J with a certain parameter QJI, go to state K with parameter QKI, then we can get how long on average we're going to stay in state I, because it's going to depend upon which alarm clock goes off first. So let's remember our exponential distribution. So each of these alarm clocks have independent exponential random variables. So each of the alarm clocks are independent exponential random variables. And we have parameters Q1I, Q2I, etc. All of these states in which we can go to from state I. So when we call from the exponential distribution, that if we have a variable that behaves according to an exponential distribution, then the minimum of all of these variables that behave according to a minimum, the minimum of all these variables also behaves according to an exponential distribution, but the rate is the sum of all of our independent ones. So remember, this is what we did with exponential distribution before. So how does this relate to our alarm clock? So let's say we're in state I. We can go to state 1, state 2. Let's say we can go to multiple different states from state I. Each one of these states we can go to has an alarm clock associated with it that behaves according to an exponential distribution. So we can think about, we have all these alarm clocks that behave according to an exponential distribution. We're going to move from state I as soon as the minimum, the first one of those rings, so the minimum rings. So that minimum, that amount of time we're going to stay in state I, behaves according to an exponential distribution with parameters sum of all of those. So what that tells us is that our holding time behaves according to an exponential distribution with rate Qi, where Qi is just the sum of all of our individual alarm clocks. So basically, the process leaves state I according to the sum of all the rates. Okay, so now what probability? Where are we going to go? So here we know the holding time. The holding time we can get just by summing up all of our rates. What's the probability I'm going to go to state J, or I'm going to go to state K? So probability, for instance, that I'm going to go to state J from state I is if that IJ clock rings first. The IJ clock rings first, then I'm going to go to state J. If the IK clock rings first, I'm going to go to state K. So remember from the exponential distribution, when is it that our variable is the minimum of all these other variables? So here we can think about, we want our IJ clock to be in the minimum of all of our other clocks. So the way that we can write this is the probability that our IJ clock rings first is going to be the rate for our IJ clock, which was QJI, divided by the entire sum of all of our rates. So here's the sum, QKI, for all of those Ks, which we can reach from state I. So the probability the state I moves to state J is simply the parameter QJI, the transition rate from I to J, divided by that holding time parameter for state I, the sum of all of those parameters. This gives our embedded chain transition probabilities. Okay, so I'm going to pause this just for a second. Okay, so now let's consider this example. So this is a Markov chain. Here we can go from any of our states to any of our other states. We can go from state 1 to state 2 or state 3. The rate at which we go from state 1 is given by Q21. The rate at which we go from state 1 to state 3 is given by Q31, etc. So here we can figure out what our holding times are for each of our states. So the holding time parameters for Q1 is given by the sum of both of our transitions. So I can go from 1 to 2 or 1 to 3. So I sum up those transition rates, and that gives us the holding time parameters for Q1. Similarly, Q2 I can go from 2 to 1 or 2 to 3, so I sum up those transition rates, etc., etc. So we can also get the probability that we're going to go from state 1 to state 2 or state 1 to state 3. So here, remember, our transition matrix for our embedded chain always has 0 because we're always thinking about we're moving from one state to the other state. So what's the state that we're going to get to? So here, what's the probability I'm going to go from state 1 to state 2? Well, it's that transition rate from state 1 to state 2. I take this transition rate Q21 divided by the sum of my two transitions that I could make, or this Q1. Similarly, I can go to state 3 from state 1 according to this transition rate divided by the sum of all of the others. So similarly, if I wanted to go from 2 to 1, probability I'm going to go from 2 to 1 is this transition rate divided by the sum of both of those. Okay, so here's an example for a registration line at a college, and this is going to be a really small registration line, so you assume there's only one registrar, and it's there for people who need assistance, and so the registrar can service students at a rate of 1 student every 5 minutes, and then students arrive according to a process at a rate of 1 student every 4 minutes. We assume that they cannot have a line longer than 4 people, so if there's 4 people in line, then the student walks away and tries again later, and as soon as there's 1 person in line, the registrar starts working. And again, we assume all the arrival times are independent of the service time. So we let xt be the number of students in the line at time t, so it could be 0 all the way up to 4 because it's capped at 4. Then xt is a continuous time Markov chain. So if there's no one in line, then the size of the line increases to 1 when a student arrives. If there's 4 people in line, then it can only decrease to 3 whenever the registrar finishes. And if we're anywhere between 0 and 4, so if we have 1, 2, or 3, then we can either decrease if the registrar finishes, or we can increase if a student arrives. So here, if the student arrives before the registrar is finished, then it's going to increase by 1, whereas the registrar gets done before another student arrived, and it decreases by 1. So we can imagine that if there's 1 student in line, then there's 2 clocks that have been started. So there's a clock associated with the registrar finishing, and there's a clock associated with the student arriving. So the student arrives at rate 1/4, so one student every 4 minutes. The registrar's service time is 1 student every 5 minutes, so it has a rate of 1/5. So if the arrival time rings first, so if another student arrives first, then the line increases by 1. If the registrar finishes, then the line is going to decrease by 1. So the same dynamics are for 2 or 3 people in line. We basically have this transition diagram where we have our rates here. So if we have no students, then we're always going to move up to 1 student at a rate of 1/4. If we have 1 student, then we can move down to no students at a rate of 1/5, our service time. We can move up to 1/4 at the rate of our arrival time. And the same is true except for here, if we're in state 4, then we assume it's capped at that, so we can only decrease at a rate of 1/5, the rate the registrar finishes. So again, here's our transition diagram. We can get our holding time parameters. So here, remember the way that we get our holding time parameters is we sum up all of our rates. So from 0, the only thing that we can do is we can go to 1. So we're just going to have the rate 1/4. If we're at 1, 2, or 3, then we can either go up or down. So we can go down at a rate of 1/5, up at a rate of 1/4, so we're going to add those. If here we're in 4, we can only go down at a rate of 1/5, so we get our holding time parameters. For Q0, it's 1/4. For Q4, it's 1/5. For everything else, it's going to be the 1/4 plus the 1/5, which is 9/20. So using these, we can talk about our embedded chain transition matrix. So this is the probability of going from, let's say, 0 to 1, probability of going from 1 to 2 or 1 to 0, etc., etc. So here, these are our transition probabilities, so it has to sum up to 1. Notice we can only go from 0 to 1, so this should be a 1, and it is because we take the rate at which we go divided by the sum of all the rates. We have 1/4 over 1/4. The probability that we're going to go from 1 to, let's say, 2 here is we take this rate, 1/4, divided by the sum of the 2 rates. So we're going to have 1/4 divided by our 9/20, which is going to give us 5/9. Probability that we're going to go down would be this rate of 1/5 divided by the sum of both rates, which is 9/20, so we're going to have 4/9. Notice this does add to 1 because we have to go somewhere from state 1. So this is an example of what could happen. So here, this is our states. We have 0 people all the way down to 4 people. This is as we go across time. So here we have, this is 60 minutes. So we start off with no people, and we stay with no people for a certain period of time. One person arrives, the register starts working, and so the register gets done before another student arrives. We go back up here to 0 people, and then a student arrives, and so then the register starts working on the one student, but another student arrives before they get done. Still the register is not done, another student arrives. We keep at 3 people for a while, and then the register gets done, and we move back up to 2, etc., etc. So the students arrive faster than the register service time, so the line does tend to grow over time, as you would expect. And this is a special case of what's called birth and death processes, which we're going to talk about later. So the next lecture, we're going to finish the infinitesimal generator matrix, and so we're going to actually put all these rates and figure out how to use these rates to get our infinitesimal generator matrix.